Hello there, and welcome to my channel, where we drift gently through the cosmos, one mystery at a time. Tonight, we're embarking on a quiet journey into something extraordinary, something that's happening all around you right now. As you listen to these words, invisible particles from the deepest reaches of space are streaming through your body, through your walls, through the very ground beneath your feet. They've traveled millions, perhaps billions of years to reach you, carrying stories from dying stars, exploding supernovas, and the violent hearts of distant galaxies. These are cosmic rays, the universe's most persistent messengers, and tonight we'll uncover their secrets together. Now, I should warn you, this exploration might be just fascinating enough to keep you awake. But if that happens, well, at least you'll drift off knowing something remarkable about the invisible rain that's been falling on Earth since before life itself began. So settle in, make yourself comfortable, and let your thoughts float as we discover what cosmic rays really are, where they come from, and how they've been shaping our world in ways you've never imagined. Before we begin our cosmic journey, I'd love to know where in the world you're listening from and what time it is for you right now, whether it's midnight in Melbourne or 3 a.m. in Manchester. This invisible cosmic shower is reaching you wherever you are, and there's something rather poetic about that, isn't there? That we're all connected by this gentle bombardment from space. If you enjoy these slow explorations of science, please consider giving this video a like and subscribing to the Sleepy Scientist. It helps more curious minds find their way here, and it means the world to me. Also, a gentle reminder, this video is for educational and relaxation purposes only, and isn't intended as medical advice. If you have any health concerns, please consult a qualified professional now. Then, shall we step into the invisible rain? Picture this. You're standing in your garden on a perfectly clear night. The stars are twinkling overhead, and everything seems peaceful and still. But if you could see the invisible, what would appear before your eyes would be one of the most spectacular light shows in the universe, a constant shower of particles streaming down from every direction, at nearly the speed of light, some no bigger than a single proton, others carrying more energy than a professional tennis serve, all of them visitors from the cosmic deep. This is the reality of cosmic rays. Though the name is a bit misleading, they're not rays at all in the way we think of light rays. Instead, they're actual particles, mostly protons, the nuclei of hydrogen atoms, but also heavier atomic nuclei, electrons, and even exotic particles we rarely see on Earth. They arrive at our planet after journeys that would make even the most seasoned traveler dizzy with wonder. Some have been racing through space for just a few years, others for millions of years, and a few, the real cosmic wanderers, have been traveling since before our solar system even existed. Every second of every day, about 1,000 of these particles pass through each square meter of Earth's atmosphere. That means right now, as you lie there listening, roughly 10,000 cosmic rays are streaming through your body. The minute you can't feel them, you can't see them, but they're there. Silent visitors from the stars, carrying with them the signatures of some of the most violent and energetic events in the universe. The story of cosmic rays begins over a century ago, with a man who quite literally reached for the sky to solve a puzzle that was keeping physicists awake at night. In the early 1900s, scientists knew that the air around us was slightly radioactive. They could measure it with their instruments, but they couldn't figure out why the obvious assumption was that this radiation came from radioactive elements in the Earth's crust. After all, radium and other radioactive materials had recently been discovered, and they were known to emit particles that could ionize air, making it conductive. But there was a problem. If the radiation came from the ground, then the higher you went, the less radiation you should detect. The Earth's radioactive influence should fade with altitude, like the warmth from a campfire growing fainter as you step away from it. Several scientists tested this idea by taking their instruments up in balloons, and at first it seemed to work. the radiation did decrease as they climbed higher, confirming what everyone expected. Then along came Victor Hess, an Austrian physicist with a passion for precision and an apparently fearless attitude toward balloon rides in 1912. Hess decided to take his radiation detectors much higher than anyone had gone before. He ascended to over 5 kilometers above the Earth's surface, where the air is thin and cold, and the view spectacular. What he found there changed our understanding of the universe forever. Instead of the radiation continuing to decrease as he climbed higher, Hess discovered something remarkable. Above about 1.5 kilometers, the radiation began to increase. The higher he went, the more intense it became. This was completely backwards from what everyone expected. If the radiation came from the Earth, it should have been weakest at high altitude, not strongest. Hess realized he had discovered something profound. The radiation wasn't coming from below. It was coming from above, from space itself. He called this mysterious radiation cosmic rays, and though we now know they're particles, not rays, the name stuck. Hess had opened a window into the high-energy universe and discovered that space is not the empty void we once imagined, but a dynamic, energetic place filled with particles racing at incredible speeds. His discovery would eventually earn him the Nobel Prize in Physics and launch an entirely new field of scientific investigation. But what exactly are these cosmic rays, and where do they come from? The answer takes us on a journey to some of the most extreme environments in the universe, places where matter is compressed to unimaginable densities, where magnetic fields twist and writhe with the power of 1 trillion lightning bolts, and where explosions release more energy in seconds than our sun will produce in its entire 10 billion year lifetime. The vast majority of cosmic rays, about 90%, are protons, the simplest and most common atomic nuclei in the universe. These are essentially hydrogen atoms stripped of their electrons, leaving just the positively charged proton core. Another 9% are alpha particles, which are helium nuclei, containing 2 protons and 2 neutrons. The remaining 1% is a exotic mix, heavier nuclei from carbon and oxygen all the way up to iron and beyond, along with electrons, and even stranger, particles like muons and neutrinos. What makes cosmic rays remarkable isn't just what they are, but how much energy they carry. The average cosmic ray proton reaches Earth with about 1 billion electron volts of energy. That might not sound like much, but remember, we're talking about a single subatomic particle carrying energy equivalent to a flying mosquito concentrated into a space trillions of times smaller. And that's just the average. Some cosmic rays carry energies that boggle the mind. The most energetic cosmic ray ever detected struck Earth's atmosphere in 1991 with an energy of about 3 times 10 to the 20th electron volts. That's roughly the energy of a baseball traveling at 60 miles per hour, all concentrated in a single proton. Scientists nicknamed this particle the "oh my god" particle because that was reportedly the reaction of the physicist who first analyzed the data. It had so much energy that it challenged our understanding of physics itself. Where in the universe could such a particle possibly come from? And how could it have been accelerated to such incredible speeds? These ultra-high energy cosmic rays remain one of the greatest mysteries in astrophysics. When to understand where cosmic rays come from, we need to think about the most violent events in the cosmos. Most cosmic rays are thought to be accelerated by shock waves, the same basic physics that creates a sonic boom when a jet breaks the sound barrier. But in space, these shock waves are created by some of the most dramatic events imaginable. Supernova explosions are probably the most important cosmic ray factories in our galaxy. When a massive star reaches the end of its life, it doesn't go gently into that good night. Instead, it explodes with the force of billions of suns, releasing more energy in a few seconds than our sun will produce. In its entire lifetime, the explosion creates a shock wave that races outward at thousands of kilometers per second. When this shock wave encounters particles in space, It acts like a cosmic particle accelerator, boosting them to incredible energies and flinging them across the galaxy. But supernovas aren't the only cosmic ray sources. Active galactic nuclei, the supermassive black holes at the centers of some galaxies, can launch jets of particles at nearly the speed of light. These jets, powered by matter falling into the black hole, can extend for millions of light years and accelerate particles to energies that dwarf even the most powerful human-made accelerators. Gamma-ray bursts, the most energetic explosions in the universe. After the Big Bang itself, are another potential source. These brief but incredibly intense flashes of gamma radiation are thought to occur when massive stars collapse into black holes, or when neutron stars collide. The energies involved are so enormous that they can be detected across the entire observable universe. Closer to home, our own sun produces cosmic rays, though much lower energy ones. Solar flares and coronal mass ejections can accelerate particles and send them streaming toward Earth. These solar cosmic rays are usually much less energetic than their galactic cousins, but they can still be significant, especially for astronauts and airline crews who spend time at high altitudes where Earth's protective atmosphere is thinner. The journey of a cosmic ray from its source to Earth is an epic tale of cosmic proportions. Imagine a proton accelerated by a supernova shockwave 20,000 light-years away. It begins its journey racing through space at 99.9% the speed of light, but space isn't empty. It's filled with magnetic fields that twist and turn the particle's path like a pinball bouncing between bumpers. Our galaxy, the Milky Way, has its own magnetic field, and cosmic rays get trapped and deflected by it, causing them to spiral and bounce around for millions of years before they either escape into intergalactic space or eventually find their way to a planet like Earth. This means that by the time a cosmic ray reaches us, it has likely forgotten which direction it came from its path, so twisted and turned by magnetic fields that we can't trace it back to its source. For the highest energy cosmic rays, the ones with energies beyond what galactic sources can easily explain, the journey may be even more remarkable. These particles might come from other galaxies entirely racing across the vast emptiness of intergalactic space for hundreds of millions of years before happening to intersect with our tiny planet. The fact that we detect them at all is a testament to the incredible violence and energy of their cosmic birthplaces. As our cosmic ray finally approaches Earth, after its long journey through space, it encounters our planet's first line of defense against high-energy radiation, the magnetosphere. This invisible magnetic bubble extends far out into space, created by our planet's molten iron core acting like a giant dynamo. The magnetosphere deflects many cosmic rays, especially the lower energy ones, back into space like a cosmic shield. But Earth's magnetic field isn't perfect. It has weak spots, particularly near the poles where the field lines converge. This is why cosmic ray intensity is higher at the polar regions, and why phenomena like the aurora occur when particles from space interact with our atmosphere. The aurora borealis and aurora australis are actually visible reminders of the constant cosmic ray bombardment our planet receives. Those cosmic rays that do make it past the magnetosphere face one final obstacle: our atmosphere. And it's here that something truly remarkable happens. When a high-energy cosmic ray proton smashes into an air molecule high in the atmosphere, it creates a cascade of secondary particles like a cosmic billiard ball breaking apart the rack. This process, called an air shower, can involve millions or even billions of particles, all created from that single incoming cosmic ray. The atmosphere acts as a giant detector and filter, transforming the primary cosmic ray into a shower of more familiar particles, muons, electrons, photons, and neutrinos, that rain down toward Earth's surface. It's these secondary particles that we can detect with instruments on the ground, and it's through studying them that we've learned most of what we know about cosmic rays themselves. By the time this cosmic shower reaches you, Most of the particles have been absorbed or decayed, but a few muons, those heavy cousins of electrons, make it all the way to the surface and beyond. They can penetrate deep underground, traveling through rock and water with ease. In fact, muons are so penetrating that scientists use them to peer inside pyramids and volcanoes, creating X-ray-like images of structures that would be impossible to see any other way. And so ends the journey of our cosmic ray visitor, after traveling for perhaps millions of years across the galaxy, dodging magnetic fields, surviving the vacuum of space, and triggering a cascade of particles in our atmosphere. It has finally delivered its message from the cosmos, a tiny packet of information about the violent, energetic universe beyond our quiet blue world. But this is just the beginning of our cosmic ray story. These invisible messengers don't just pass through our world without leaving a trace. They've been shaping life on Earth in ways both subtle and profound from the moment the first organic molecules began to organize themselves into living systems. Cosmic rays have been there, introducing changes, pushing evolution in new directions, and occasionally causing catastrophes that reset the biological clock. And yet, for all their cosmic drama, cosmic rays are remarkably democratic in their visitation. They don't discriminate between rich and poor, young and old, city dweller or countryside farmer. They simply are everywhere. All the time, a constant, gentle bombardment that connects every living thing on Earth to the wider universe in ways that are both profound and surprisingly intimate. Let's pause for a moment and consider what this means for you personally right now. As you lie there listening to these words, cosmic rays are streaming through your body at a rate of about 10,000 per minute, each one a messenger, from some distant corner of the galaxy, perhaps accelerated by a star that exploded when the first fish were learning to swim in primordial seas, or when the first flowers were blooming on ancient continents. These particles carry with them the atomic signatures of their birthplaces, traces of iron forged in stellar cores, or carbon created in the heart of a dying star. Your body is remarkably transparent to cosmic rays. They pass through you as easily as light passes through a clean window. Most of them don't interact with your atoms at all. They simply zip through the spaces between your cells, like ghostly visitors that barely acknowledge your existence. But occasionally, just occasionally, one will collide with an atom in your DNA or some other crucial molecule. And when that happens, something changes. Now, before you start worrying, let me put this in perspective. The dose of radiation you receive from cosmic rays is actually quite small, about the same as you'd get from eating a few bananas or taking a cross-country flight. It's part of the natural background radiation that life on Earth has evolved with for billions of years. In fact, cosmic rays may have played a crucial role in evolution itself, providing just enough genetic mutation to keep life interesting and adaptable without causing catastrophic damage. Some scientists have proposed that cosmic rays might have been one of the driving forces behind the great leaps in evolutionary complexity, the emergence of complex cells, the explosion of multicellular life, the development of intelligence. These aren't sudden random events, but rather the result of countless small changes accumulating over vast periods of time, and cosmic rays, with their ability to introduce subtle genetic modifications, may have been one of the gentle nudges that pushed life toward greater complexity. There's even a hypothesis that cosmic rays might influence cloud formation and thus climate on Earth. When cosmic rays enter the atmosphere, they create ions, charged particles that can serve as nucleation sites for water droplets. If this is true, then changes in cosmic ray intensity, perhaps caused by our solar system's movement through different regions of the galaxy, could affect cloud cover and global temperatures. It's a beautiful example of how events in the distant cosmos might influence something as local and immediate as the weather outside your window. But cosmic rays don't just affect life. They've also become powerful tools for understanding our universe and even our own planet. Scientists have learned to use cosmic rays like X-rays to peer inside things that would otherwise remain hidden. Deep underground laboratories detect cosmic ray muons to study the fundamental particles that make up matter. Archaeologists use cosmic rays to date ancient artifacts, and geologists use them to understand how landscapes change over time. One of the most elegant examples of cosmic ray science is radiocarbon dating. Every living thing on Earth contains a small amount of carbon-14, a radioactive isotope created when cosmic rays interact with nitrogen in the atmosphere. Plants absorb this carbon-14 from the air, animals eat the plants, and so on, up the food chain. When something dies, it stops taking in new carbon-14, and the existing carbon-14 begins to decay at a known rate. By measuring how much carbon-14 remains in an ancient piece of wood or bone, scientists can determine how long ago it died. This technique has revolutionized archaeology and paleontology, allowing us to construct detailed timelines of human history and natural history alike, from the age of ancient civilizations to the timing of ice ages. Cosmic rays have given us a window into the past that would otherwise remain forever closed. Cosmic rays have also opened windows into the present and future. They've become essential tools for monitoring nuclear weapons testing, detecting clandestine nuclear activities, and even searching for hidden chambers in ancient monuments. The Great Pyramid of Giza, for example, has been scanned using cosmic ray muons, revealing previously unknown voids deep within its structure. These invisible particles from space have become our eyes for seeing the unseeable. In the realm of pure science, cosmic rays continue to surprise and delight researchers. They were responsible for the discovery of many fundamental particles, including the positron antimatter's answer to the electron and the muon that heavy electron cousin we mentioned earlier before we built giant particle accelerators. Cosmic rays were our primary source of high-energy particles for studying the fundamental nature of matter. Even today, with all our sophisticated technology, cosmic rays continue to reveal new secrets about the universe. The Pierre Auger Observatory in Argentina covers an area larger than Rhode Island, with detectors designed to catch the rarest and most energetic cosmic rays. These ultra-high energy particles are so rare that only about one hits each square kilometre of Earth's surface per century. But when they do arrive, they carry information about the most extreme environments in the universe, places where the laws of physics are pushed to their absolute limits. The study of cosmic rays has also led to unexpected discoveries about our own planet's history. By analysing cosmic rays trapped in ice cores from Antarctica and Greenland, scientists have reconstructed the history of our planets. The magnetic field, which acts as a shield against cosmic radiation. When the magnetic field was weaker in the past, more cosmic rays reached Earth's surface, leaving traces that we can still detect today. These cosmic fingerprints have revealed that Earth's magnetic field has flipped its polarity many times in the past, and that it may be preparing to flip again. There's something almost mystical about the idea that ice formed thousands of years ago still contains messages from space-frozen cosmic whispers that tell us about both the ancient atmosphere and the distant stars that sent their particles earthward. It's as if the planet itself has been keeping a diary written in the language of cosmic rays, waiting for us to develop the wisdom to read it. As our understanding of cosmic rays has deepened, we've also begun to appreciate their role in the broader cosmic ecosystem. They're not just random particles flying through space, they're part of a vast, interconnected system that links stars and planets, galaxies and clusters of galaxies in a web of energy and information. Cosmic rays carry energy and heavy elements from their sources and distribute them throughout the galaxy, enriching the interstellar medium with the building blocks of new stars and planets. In a very real sense, we are made of cosmic ray material, the iron in your blood, the calcium in your bones, the oxygen you breathe, all of these elements were forged in the cores of massive stars and scattered through space when those stars exploded as supernovas. The same explosions that created the cosmic rays now streaming through your body. So, in a poetic sense, cosmic rays are not just visitors from space. They're long-lost relatives carrying messages from the stellar ancestors that gave birth to the elements that make up your very being. This connection between cosmic rays and the chemical evolution of the universe is one of the most beautiful aspects of modern astrophysics. It shows how everything in the cosmos is connected, how the death of a star billions of years ago could lead to the formation of a planet, and eventually to life itself. Cosmic rays are the messengers in this cosmic story, carrying both energy and matter from their violent birthplaces to new worlds, where they might spark new forms of life and complexity. As we've learned more about cosmic rays, we've also begun to appreciate the challenges they might pose for future space exploration beyond Earth's protective magnetosphere and atmosphere. Cosmic rays pose a significant hazard to astronauts. The Apollo astronauts reported seeing flashes of light even with their eyes closed, caused by cosmic rays passing through their retinas. These same particles can damage electronics, disrupt computer systems, and over long periods, increase the risk of cancer and other health problems. This has led to intensive research into cosmic ray shielding and protection for future missions to Mars and beyond. Some proposals involve surrounding spacecraft with thick layers of material to absorb cosmic rays. Others suggest using magnetic fields to deflect them, much like Earth's magnetosphere does. There are even ideas for using the spacecraft's fuel or water supplies as shielding material, serving double duty as both protection and life support. But perhaps the most intriguing aspect of cosmic rays is what they tell us about the universe's capacity for violence and beauty in equal measure. The same supernova explosion that creates these high-energy particles also enriches space with heavy elements and triggers the formation of new stars. The same galactic magnetic fields that trap and accelerate cosmic rays also help protect star-forming regions from too much harmful radiation. It's a delicate balance between creation and destruction that has allowed the universe to evolve from a simple sea of hydrogen and helium into the rich, complex cosmos we see today. There's also something humbling about cosmic rays. They remind us that despite all our technology and knowledge, we live in a universe that operates on scales. We can barely comprehend energies that dwarf our most powerful machines, and timescales that make human history seem like a brief flicker. They connect us to events and places so distant and extreme that they challenge our ability to understand them. Yet here they are, passing through us every moment of every day. Silent witnesses to the grandeur and mystery of the cosmos. As you drift off to sleep tonight, perhaps you'll think differently about the invisible rain falling around you. Those cosmic rays aren't just abstract scientific curiosities. They're tangible connections to the wider universe. Each one a story of cosmic violence and stellar death. Each one a messenger carrying information about places and events beyond our direct experience. They're proof that we don't live in isolation, but are part of something vast and interconnected, something beautiful and terrible and utterly magnificent. The study of cosmic rays continues to evolve, with new detectors and techniques revealing ever more subtle aspects of these cosmic messengers. Space-based observatories free from the filtering effects of Earth's atmosphere are beginning to measure cosmic rays directly before they interact with our planet. Ground-based arrays covering thousands of square kilometers are catching the rarest and most energetic cosmic rays, and sophisticated computer simulations are helping us understand how these particles interact with matter and magnetic fields throughout their long journeys. Each new discovery raises new questions about the nature of cosmic ray sources the mechanisms of particle acceleration, and the role of cosmic rays in the broader evolution of the universe. We're still learning about how cosmic rays affect the formation of stars and planets, how they influence the development of galactic magnetic fields, and how they might even play a role in the emergence and evolution of life itself. In the quiet laboratories scattered across our planet, scientists work day and night to catch these elusive visitors from space. What they've discovered is that cosmic rays are far more complex and fascinating than Victor Hess could ever have imagined when he first detected them drifting high above the Austrian countryside more than a century ago. The modern study of cosmic rays has revealed layers upon layers of mystery, each discovery opening new questions about the nature of our universe. Deep beneath the mountains of Italy, Japan, and the United States, underground laboratories shield sensitive detectors from the constant shower of cosmic ray particles above ground. These subterranean sanctuaries allow scientists to study the most penetrating cosmic rays, the ones that can travel through kilometers of solid rock, as if it were barely there. These deep underground facilities have become windows into some of the most exotic physics in the universe, revealing particles and interactions that exist nowhere else in our everyday experience. One of the most remarkable things about these underground cosmic ray detectors is their size. Some cover areas larger than football fields, filled with thousands of tons of ultra-pure water or liquid scintillator, waiting patiently for the rare cosmic ray that makes it through the Earth's crust. When such a particle finally arrives, it creates a brief flash of light, captured by arrays of sensitive photomultiplier tubes that can detect even a single photon. These underground cathedrals of science represent some of humanity's most ambitious attempts to eavesdrop on the conversations between particles from distant stars. But perhaps even more impressive are the cosmic ray observatories that sprawl across the Earth's surface, like the Pierre Auger Observatory in Argentina, which we mentioned earlier, or the Telescope Array project in Utah. These installations cover thousands of square kilometers, with networks of detectors all synchronized to catch the brief shower of particles that results when an ultra-high energy cosmic ray collides with our atmosphere. The scale of these projects is breathtaking. Individual detector stations, separated by kilometers, all working together to reconstruct the path and energy of a single particle that traveled across the galaxy to reach us. The data these observatories collect tells us stories that read like science fiction. A cosmic ray proton with the energy of a well-hit tennis ball, concentrated into a space smaller than an atomic nucleus, particles that have been accelerated to energies that our most powerful machines can't even approach. These ultra-high energy cosmic rays push the boundaries of known physics and force us to consider acceleration mechanisms that operate on scales we can barely imagine. Some of these cosmic rays carry so much energy that they shouldn't be able to reach us at all. According to our understanding of physics, particles with such extreme energies should interact with the cosmic microwave background. Radiation, the faint afterglow of the Big Bang that fills all of space. These interactions should slow down the particles and limit how far they can travel. Yet here they are, arriving at Earth with energies that seem impossible. This puzzle, known as the GZK cutoff, after the pair scientists who predicted it, remains one of the great mysteries in cosmic ray physics. The search for the sources of these ultra-high energy cosmic rays has led astronomers to consider some of the most exotic objects in the universe. Supermassive black holes at the centers of galaxies that can launch jets of material at nearly the speed of light gamma ray bursts that release more energy in seconds than our sun will produce in billions of years. The collision of neutron stars that creates ripples in space-time itself. Each of these phenomena represents physics at its most extreme, where matter and energy behave in ways that challenge our understanding. But cosmic rays don't just tell us about distant, violent events. They also provide a unique perspective on our own cosmic neighborhood, by studying how cosmic rays are deflected and modulated by the solar wind, the stream of particles flowing out from our sun. Scientists can map the magnetic environment of our solar system in ways that would be impossible with any other technique. Cosmic rays act like tiny compass needles, revealing the invisible magnetic fields that permeate space around us. The 11-year cycle of solar activity creates a corresponding cycle in cosmic ray intensity. As the sun becomes more active, its magnetic field strengthens and more cosmic rays are deflected away from the inner solar system during solar POM. Minimum when the sun is quiet, more cosmic rays reach Earth. This solar modulation of cosmic rays provides a natural laboratory for studying how magnetic fields interact with charged particles on a scale much larger than anything we can create on Earth. There's also growing evidence that cosmic rays might influence Earth's atmosphere and climate in subtle but important ways. As cosmic rays create ions in the upper atmosphere, these ions can serve as nucleation sites for cloud the formation. Some scientists have proposed that changes in cosmic ray intensity caused by our solar system's movement through different regions of the galaxy might affect cloud cover and thus global climate over very long timescales. This connection between cosmic rays and climate remains controversial, but it highlights how events in deep space might influence something as immediate and local as the weather. The biological effects of cosmic rays are another area of active research. While the radiation dose from cosmic rays at Earth's surface is relatively small, it's not negligible. Cosmic rays are one of the sources of background radiation that all life on Earth has evolved with. They contribute to the natural mutation rate that drives evolution, and they may have played a role in some of the major transitions in the history of life on our planet. Some researchers have even suggested that cosmic rays might have been involved in the mass extinction events that have periodically reset life on Earth if our solar system passed through a region of space with unusually high cosmic ray intensity. Perhaps due to a nearby supernova explosion, the increased radiation could have damaged the ozone layer, leading to increased ultraviolet radiation at the surface. This scenario remains speculative, but it illustrates how cosmic rays connect the fate of life on Earth to events occurring throughout the galaxy. For astronauts venturing beyond Earth's protective magnetosphere, cosmic rays represent one of the most significant challenges for long-duration space missions. The radiation environment in deep space is harsh, with cosmic rays providing a constant background of high-energy particles that can damage both equipment and human tissue. NASA and other space agencies have invested heavily in understanding cosmic ray radiation and developing ways to protect future explorers. The challenge is that cosmic rays are incredibly difficult to shield against. Unlike lower-energy radiation, that can be stopped by relatively thin layers of material, cosmic rays can penetrate almost anything practical spacecraft shielding. Might reduce the cosmic ray dose, but it can't eliminate it entirely. This has led to research into novel shielding concepts, including magnetic shields that would mimic Earth's magnetosphere and biological countermeasures that might help repair cosmic ray damage to living tissue. One of the most intriguing aspects of cosmic ray research is how it connects to our understanding of dark matter, that mysterious substance that makes up most of the matter in the universe, but interacts only weakly with ordinary matter. Some theories predict that dark matter particles might occasionally collide with cosmic rays or interact with them in other subtle ways. Deep underground cosmic ray detectors, originally built to study neutrinos and other exotic particles, become some of our most sensitive tools for searching for dark matter. The search for dark matter through cosmic rays represents one of the most ambitious detective stories in modern science. Scientists are looking for tiny deviations from the expected cosmic ray spectrum, subtle excesses or deficits that might reveal the presence of dark matter particles annihilating or decaying in the halo of our galaxy. These signals would be incredibly faint, buried in the noise of ordinary cosmic ray interactions, but they might provide our first direct evidence of dark matter's existence. Cosmic rays have also become messengers from some of the most extreme environments in the universe. Neutron stars, where matter is compressed to densities that exceed atomic nuclei. Black holes, where space-time is warped beyond recognition. The black hearts of active galaxies, where supermassive black holes devour matter and launch jets across millions of light years. Each cosmic ray carries information about the conditions at its source, encoded in its energy spectrum composition and arrival direction. The challenge is learning to read these cosmic messages. The magnetic fields that permeate our galaxy scramble the paths of cosmic rays, making it nearly impossible to trace them back to their sources directly. It's like trying to determine where a ball came from after it's bounced off a dozen walls in a pitch-black room. The energy and composition of cosmic rays provide clues about their origins, but unraveling these clues requires sophisticated theoretical models and careful comparison with observations. Some of the most energetic cosmic rays might come from outside our galaxy entirely. These extragalactic cosmic rays would have traveled across the vast emptiness of intergalactic space for hundreds of millions of years before reaching us. They carry information about the most energetic processes in the universe and about the structure of intergalactic magnetic fields that we have no other way to study. The fact that we can detect particles that have traveled such vast distances and carried information across such enormous spans of time is truly remarkable. It's as if the universe has its own postal system with cosmic rays serving as letters sent from distant civilizations of stars and galaxies. Most of these letters take so long to arrive that their senders have long since changed or disappeared entirely, but the messages they carry are still readable, still full of information about places and times we could never visit directly. As our understanding of cosmic rays has grown, so has our appreciation for their role in the cosmic ecosystem. They're not just random particles flying through space. They're part of a vast interconnected system that shapes the evolution of galaxies, regulates star formation, and influences the development of planetary atmospheres. Cosmic rays carry energy and momentum throughout the galaxy, stirring up the interstellar medium and preventing it from collapsing too quickly under its own gravity. This cosmic ray pressure is thought to be one of the factors that regulates star formation in galaxies. If there were no cosmic rays, gas clouds might collapse more easily, leading to rapid bursts of star formation that would quickly exhaust a galaxy's supply of raw materials. Instead, cosmic rays provide a kind of pressure that slows down the collapse, allowing star formation to proceed at a more measured pace over billions of years. The heavy nuclei in cosmic rays also play a crucial role in the chemical evolution of the galaxy. These particles carry the products of stellar nucleosynthesis: iron, cobalt, nickel, and other heavy elements forged in the cores of massive stars and scattered into space. When those stars exploded, cosmic rays transport these elements throughout the galaxy, mixing them into the interstellar medium where they become available for incorporation into new generations of stars and planets. In this sense, cosmic rays are gardeners of the galaxy, tending to the interstellar medium and ensuring that the chemical elements necessary for life are distributed widely rather than remaining concentrated near their stellar birthplaces. Without cosmic rays, the galaxy might be a much less hospitable place, with heavy elements locked away in isolated regions and vast stretches of space containing only the primordial hydrogen and helium left over from the Big Bang. The study of cosmic rays has also led to unexpected insights about the nature of time and space itself. The highest energy cosmic rays challenge our understanding of fundamental physics. They carry energies that approach the theoretical limits imposed by quantum mechanics and relativity. When particles reach such extreme energies, the familiar rules of physics begin to break down, and new phenomena may emerge. Some theories predict that at the highest energies, space-time itself might become granular, like a fabric viewed under extreme magnification cosmic rays. with energies near these theoretical limits might serve as probes of this quantum structure of space-time, carrying information about the fundamental nature of reality itself. The fact that such particles exist and can be detected suggests that the universe operates as a natural laboratory for exploring physics beyond the reach of any human-made experiment. There's something deeply humbling about cosmic rays. They remind us that despite all our technological achievements and scientific understanding, we are still small creatures on a small planet in a vast and energetic universe. Every cosmic ray that passes through your body carries more energy than the most powerful laser we've ever built. Yet, these particles are so common that billions of them stream through you every day without you noticing. This perspective cosmic rays provide on our place in the universe is both humbling and inspiring. It reminds us that we are connected to the stars not just through the chemical elements in our bodies, but through the constant, gentle bombardment of particles that links us to the most energetic events in the cosmos. We are not isolated observers of the universe. We are participants in it, bathed in radiation from distant stars and shaped by forces that operate on galactic scales. As you listen to these words, drifting perhaps towards sleep, cosmic rays continue their ancient dance around and through you, each one a messenger from the deep cosmos, each one carrying information about places and events beyond our direct experience. They connect you to supernova explosions that occurred before the Earth formed, to black holes spinning in the hearts of distant galaxies, to the very structure of space-time itself. In a universe that often seems cold and empty, cosmic rays remind us that space is alive with energy and motion. They are proof that the cosmos is not a static, unchanging void, but a dynamic, evolving system where matter and energy flow from star to star, from galaxy to galaxy, creating connections that span the observable universe. These invisible messengers have been falling like gentle rain since before the first molecules organized themselves into life, and they will continue long after the last star burns out. The beauty of cosmic rays lies not just in their exotic origins or extreme energies, but in their democracy. They don't choose their destinations based on wealth or status, knowledge or ignorance. They simply arrive everywhere at all times, creating a shared experience that unites every living thing on Earth. The cosmic ray that just passed through your chest might have been accelerated by the same supernova shockwave that created the particles streaming through a whale in the Pacific Ocean, or a bird flying over the Sahara Desert, or a tree growing in the Amazon rainforest. This universality of cosmic ray exposure has profound implications for how we think about life on Earth. Every organism that has ever existed has been shaped by these invisible visitors from space. The first primitive cells that learned to harness sunlight billions of years ago did so under a constant shower of cosmic radiation. The dinosaurs that ruled the Earth for hundreds of millions of years lived their entire evolutionary story bathed in particles from dying stars. The early humans who first looked up at the night sky and wondered about their place in the cosmos were themselves walking cosmic ray detectors, carrying messages from the galaxy in every cell of their bodies. Modern technology has allowed us to detect and study cosmic rays with unprecedented precision, but it has also revealed just how much we still don't understand about these cosmic messengers. For every question we answer about cosmic rays, we seem to discover two new mysteries. Lurking beneath the surface, the more we learn, the more complex and fascinating the picture becomes. Consider, for instance, the puzzle of cosmic ray composition. While most cosmic rays are simple hydrogen nuclei protons, the small percentage that consists of heavier elements tells a story of stellar evolution and galactic chemistry that we're only beginning to understand. The ratio of different elements in cosmic rays doesn't match what we see in ordinary matter, suggesting that the acceleration processes that create cosmic rays are selective, favoring some elements over others. But why this happens and how it works remains one of the great unsolved problems in cosmic ray physics. Then there's the mystery of cosmic ray. Anisotropy? If cosmic rays came from sources distributed randomly throughout the galaxy, we would expect them to arrive at Earth from all directions. Equally but careful measurements have revealed tiny but significant deviations from this perfect isotropy cosmic rays seem to arrive slightly more frequently from some directions than others. These anisotropies are incredibly small, less than 1 part in 1,000, but they're real, and they provide clues about the large-scale structure of magnetic fields in our galaxy and the locations of cosmic ray sources. The search for these subtle patterns requires enormous datasets collected over many years and sophisticated statistical techniques to separate real signals from random fluctuations. It's like trying to detect a whisper in a thunderstorm, but the results are worth the effort because they provide our only direct way to map the invisible magnetic architecture of the galaxy and to identify the cosmic accelerators that produce the highest energy particles in the universe. One of the most intriguing recent developments in cosmic ray science has been the detection of what researchers call cosmic ray electrons and positrons. These particles are much rarer than the protons that make up the bulk of cosmic rays, but they carry unique information about their sources. Electrons and positrons lose energy much more quickly than protons as they travel through space. So any cosmic ray electrons we detect must have come from relatively nearby sources, within a few thousand light years of Earth. The discovery of an excess of high-energy positrons in cosmic rays has sparked intense debate among scientists. Positrons are antimatter particles, the antiparticles of electrons, and they shouldn't be common in a universe dominated by ordinary matter. Some scientists have proposed that these excess positrons might be evidence of dark matter particles annihilating in the halo of our galaxy, while others suggest they come from pulsars, rapidly rotating neutron stars that can accelerate particles to high energies. This debate illustrates one of the most exciting aspects of cosmic ray science. The field sits at the intersection of particle physics, astrophysics, and cosmology. Cosmic rays provide a unique laboratory for studying fundamental physics under conditions that can't be reproduced on Earth. They carry information about the most extreme environments in the universe, and they might even provide clues about the nature of dark matter and other unsolved mysteries in physics. The technological challenges of detecting and studying cosmic rays have driven innovations that benefit many other fields of science. The sensitive detectors developed for cosmic ray observatories have found applications in medical imaging and industrial inspection. The data analysis techniques used to extract signals from cosmic ray noise have influenced fields ranging from finance to biology, and the large-scale international collaborations that characterize modern cosmic ray science have become models for other big science projects. Space-based cosmic ray detectors have opened entirely new windows on the cosmic ray universe, free from the filtering and distorting effects of Earth's atmosphere. These instruments can measure cosmic rays directly before they interact, with air molecules providing much cleaner data about cosmic ray composition and energy spectra. The Alpha Magnetic Spectrometer installed on the International Space Station has been collecting cosmic ray data for over a decade, producing some of the most precise measurements ever made. But space-based detectors face their own challenges. The harsh radiation environment of space can damage sensitive electronics. Cosmic rays themselves can interfere with detector operation, and the limited size and weight constraints of space missions mean that space-based detectors are much smaller than their ground-based counterparts. Each type of detector, ground-based and space-based, provides complementary information, and the combination of different approaches gives us the most complete picture of cosmic rays. The study of cosmic rays has also benefited from advances in computer simulation. Modern supercomputers can model the complex processes that occur when cosmic rays interact with matter and magnetic fields. These simulations help scientists understand how cosmic ray showers develop in the atmosphere, how particles are accelerated at supernova shock fronts, and how cosmic rays propagate through the galaxy. These computational models are essential because cosmic ray physics involves processes that operate over enormous ranges of scale, from the quantum mechanical interactions between individual particles to the galactic scale dynamics of magnetic fields and shock waves. No single experiment or observation can capture this full range. So theoretical models provide the framework that ties together different types of measurements and helps scientists interpret what they see. One of the most ambitious recent projects in cosmic ray science has been the development of what researchers call multi-messenger astronomy. This approach combines cosmic ray observations with measurements of electromagnetic radiation, gravitational waves, and neutrinos to study the same astronomical objects and events from multiple perspectives. When a supernova explodes, it produces not only cosmic rays but also light neutrinos and gravitational waves. By coordinating observations across all these different channels, scientists can build much more complete pictures of these cosmic events. The recent detection of gravitational waves from colliding neutron stars, accompanied by observations of light and gamma rays from the same event, has demonstrated the power of this multi-messenger approach. These neutron star collisions are thought to be sources of some of the heaviest cosmic ray nuclei, as well as the sites where many of the universe's gold, platinum, and other precious metals are created. The ability to study these events through multiple channels provides unprecedented insight into some of the most extreme physics in the universe. Cosmic rays have also become important tools for studying our own planet's history. The interaction of cosmic rays with Earth's atmosphere produces radioactive isotopes that get incorporated into ice sheets, tree rings, and other natural archives. By measuring the abundance of these cosmogenic isotopes, scientists can reconstruct changes in cosmic ray intensity over thousands of years and use this information to study past changes in solar activity, Earth's magnetic field, and even nearby supernova explosions. This field of cosmogenic nuclide research has revealed that Earth has been subjected to periods of enhanced cosmic ray bombardment. In the past, some of these events coincide with known changes in climate or biological diversity, suggesting that cosmic rays might have played a role in shaping Earth's environmental history. The connection between cosmic events and terrestrial changes is still being explored, but it highlights how our planet's history has been influenced by forces operating throughout the galaxy. The future of cosmic ray science looks incredibly promising. New detector technologies are being developed that will be able to measure cosmic rays with unprecedented precision and sensitivity. The planned Cherenkov telescope array will use hundreds of telescopes working together to study the highest energy cosmic rays and gamma rays with sensitivity far beyond current instruments. New space-based detectors are being designed to measure cosmic ray composition and energy spectra with much greater accuracy than ever before. Perhaps most exciting are the prospects for detecting cosmic neutrinos and gravitational waves from the same sources that produce cosmic rays. Neutrinos are ghostly particles that barely interact with matter, allowing them to travel from their sources to Earth in straight lines undeflected by magnetic fields. If scientists can detect neutrinos from cosmic ray sources, they will finally be able to pinpoint where cosmic rays come from and study the acceleration mechanisms in detail. Gravitational waves provide another new window on cosmic ray sources. The violent events that accelerate particles to cosmic ray energies also produce ripples in space-time that can be detected by instruments like LIGO and Virgo. As these gravitational wave detectors become more sensitive, they will be able to study more and more cosmic ray sources, providing new insights into how these cosmic accelerators work. The search for the sources of ultra-high energy cosmic rays remains one of the holy grails of cosmic ray science. These particles carry energies that approach the theoretical maximum allowed by physics. Yet we still don't know where they come from or how they are accelerated. New detector arrays covering tens of thousands of square kilometers are being planned to catch more of these rare events and provide better statistics for identifying their sources. There's also growing interest in using artificial intelligence and machine learning techniques to analyze cosmic ray data. The enormous datasets produced by modern cosmic ray detectors contain subtle patterns and correlations that might be invisible to traditional analysis methods. Machine learning algorithms trained on cosmic ray data might be able to identify new types of cosmic ray sources or discover unexpected relationships between different cosmic ray properties. The potential applications of cosmic ray science continue to expand beyond pure research. Cosmic ray muons are being used to scan cargo containers for hidden nuclear materials, to monitor volcanic activity by imaging the interior of volcanoes, and to study the internal structure of buildings and archaeological sites. The penetrating power of cosmic rays makes them ideal for these applications, where other forms of radiation would be absorbed before reaching the target. In the medical field, cosmic ray research has contributed to the development of new cancer treatments. Particle beam therapy uses accelerated protons or heavier ions to destroy tumors with much greater precision than conventional radiation therapy. The techniques developed for accelerating and focusing cosmic ray particles have been adapted for medical use, providing new hope for cancer patients. Cosmic rays have even found applications in art and culture. The random nature of cosmic ray detection has inspired artists to create works based on cosmic ray data and the philosophical implications of cosmic rays. Our connection to the cosmos through these invisible messengers has influenced writers, poets, and musicians who find in cosmic rays a metaphor for the hidden connections that bind us to the universe. As we look to the future of human space exploration, cosmic rays present both challenges and opportunities. The radiation hazard they pose to astronauts on long-duration missions to Mars and beyond is a serious concern that will require innovative shielding technologies and medical countermeasures. But cosmic rays also provide a natural laboratory for studying particle physics in space, where the absence of Earth's atmosphere allows direct access to cosmic ray particles. Some visionary scientists have even proposed using cosmic rays as a source of energy for interstellar spacecraft. The idea is to capture high-energy cosmic ray protons and use them to power ion drives or other advanced propulsion systems. While this remains far beyond current technology, it illustrates how cosmic rays might play a role in humanity's eventual expansion beyond the solar system. The study of cosmic rays also raises profound questions about our place in the universe and our relationship to the cosmos. These particles connect us physically to events occurring throughout the galaxy and beyond. They remind us that Earth is not an isolated oasis in empty space, but an integral part of a dynamic, interconnected cosmic ecosystem. Every breath you take, every heartbeat, every thought that passes through your mind occurs in the context of this cosmic ray bombardment. You are literally made of stardust elements, forged in the cores of ancient stars and scattered through space by the same explosions that created the cosmic rays now streaming through your body. This is not poetic metaphor but scientific fact, a direct physical connection between you and the wider universe. The philosophical implications of this connection are staggering. If cosmic rays can influence genetic mutations and evolutionary processes, then the development of life on Earth, including the emergence of human consciousness, has been shaped by events occurring throughout the galaxy. We are not separate from the cosmos. We are products of it, participants in a vast, ongoing experiment in complexity and consciousness. Some scientists have even speculated about whether cosmic rays might carry information about other forms of life in the galaxy. If cosmic rays can transport heavy elements across vast distances, might they also carry more complex molecules? Or even simple organic compounds from one star system to another? While this remains highly speculative, it opens up fascinating possibilities for how life might spread throughout the galaxy. The democratic nature of cosmic ray exposure also has ethical implications. These particles don't recognize national boundaries or social hierarchies. They create a shared experience that unites all life on Earth in a very real sense. Cosmic rays make us all citizens of the galaxy, participants in processes that transcend any human institution or belief system. This cosmic perspective might help us develop a more mature understanding of our responsibilities as conscious beings in the universe. The same stellar processes that created the cosmic rays streaming through us also created the elements that make up our planet and everything on it. We are not masters of nature, but products of it, temporary arrangements of stardust that have somehow learned to contemplate their own origins. As our knowledge of cosmic rays continues to grow, we may discover that these invisible messengers carry even more profound secrets about the nature of the universe. They might provide clues about the fundamental structure of space-time, the existence of extra dimensions, or the ultimate fate of the cosmos. The highest energy cosmic rays probe physics at energy scales that no earthbound experiment can reach, making them natural laboratories for exploring the deepest mysteries of existence. The story of cosmic rays is still being written with each new detector that comes online, each new analysis technique that reveals hidden patterns in the data, each new theoretical insight that explains previously puzzling observations. We learn more about these cosmic messengers and their role in the grand narrative of the universe. But perhaps the most remarkable thing about cosmic rays is not their exotic origins or extreme energies, but their quiet persistence. They have been falling like gentle rain on Earth for billions of years, long before the first life forms emerged, and they will continue long after the last star burns out. They are among the most enduring features of the cosmos, patient messengers that carry information across space and time, connecting past, present, and future in an invisible web of energy and matter. Tonight, as you settle into sleep, cosmic rays will continue their ancient vigil, streaming through your dreams, carrying messages from distant supernovas and spinning black holes. They will pass through your body as they have passed through every living thing that ever existed on this planet, connecting you to the deepest mysteries and most violent beauties of the universe. In the morning, when you wake, cosmic rays will still be there, invisible companions that have shared your journey through the night. They will accompany you throughout the day, these silent witnesses to your life, just as they have witnessed the rise and fall of civilizations, the birth and death of species, the slow dance of continents across the face of the earth. There is something deeply comforting about this cosmic constancy. In a world of constant change and uncertainty, cosmic rays provide a quiet reminder that we are part of something much larger and more enduring than our individual lives. To connect us to the stars not just through the poetry of imagination, but through the solid reality of physics, through the actual particles that link our bodies to the nuclear furnaces where the elements of life were forged. The more we study cosmic rays, the more we realize how much they've shaped not just our planet, but our understanding of physics itself. These invisible visitors have been responsible for some of the most important discoveries in particle physics, often appearing in places where scientists weren't expecting them at all. In the 1932nd, physicists working with cosmic ray detectors made a discovery that would revolutionize our understanding of matter. They found something completely unexpected: particles that behaved exactly like electrons but carried positive charge instead of negative. These were positrons, the antimatter twins of electrons, and they were the first antiparticles ever detected in nature. The discovery proved that antimatter wasn't just a theoretical curiosity, but a real part of the universe, streaming down from space in the cosmic ray shower. But that was just the beginning. Cosmic rays continued to surprise scientists with a parade of new particles. In 1937, researchers found muons, those heavy cousins of electrons we've mentioned before. At the time, nobody knew what to make of them. The famous physicist Tu Rabi supposedly quipped, "Who ordered that?" when the muon was discovered. It seemed like nature was playing jokes, creating particles that didn't fit into the neat categories scientists had constructed. Then came pions, kaons, and a whole zoo of exotic particles that would eventually lead to our modern understanding of quarks and the fundamental forces. Before we had powerful particle accelerators, cosmic rays were our primary window into high-energy physics. They brought the laboratory of the cosmos right to our doorstep, delivering particles with energies we couldn't dream of creating ourselves. This history of discovery continues today. Modern cosmic ray detectors are still finding surprises, still challenging our understanding of physics. The excess of antimatter particles detected by space-based instruments has sparked debates about dark matter and exotic physics. The highest energy cosmic rays continue to puzzle scientists, carrying energies that shouldn't exist according to our current theories. There's something beautifully ironic about this. The same particles that gently rain down on us every day, mostly unnoticed, represent some of the most extreme physics in the universe. They carry energies that dwarf our most powerful machines, yet they pass through us with barely a whisper. It's as if the universe is constantly whispering its deepest secrets, but in a language so subtle we've only recently learned to listen. The detection of cosmic rays has also pushed the boundaries of technology in remarkable ways. The instruments we use to catch these elusive particles are marvels of engineering and ingenuity. Deep underground, in abandoned mines and specially constructed laboratories, arrays of photodetectors wait patiently in pools of ultra-pure water. When a cosmic ray muon passes through, it creates a brief flash of blue light called Cherenkov radiation, and sensitive cameras capture this faint signal. On the surface, vast arrays of detectors spread across thousands of square kilometers monitor the atmosphere for the brief showers of particles that result when cosmic rays collide with air molecules. These ground-based observatories must distinguish the subtle signatures of cosmic ray showers from the constant background of natural radioactivity, lightning, and human-made interference. It's like trying to hear a whisper in a thunderstorm, but somehow, scientists have learned to do it. The international cooperation required for cosmic ray research is also remarkable. Because cosmic rays arrive randomly and the highest energy ones are incredibly rare, scientists need to share data across multiple observatories and time zones. The Pierre Auger Observatory, for instance, is operated by collaborations involving hundreds of scientists from dozens of countries. These researchers work together despite differences in language, culture, and politics, united by their curiosity about these cosmic messengers. This collaborative spirit extends to the data itself. Unlike many scientific fields where data is closely guarded, cosmic ray researchers have embraced open science. Much of the data collected by major observatories is freely available to anyone who wants to study it. This openness has accelerated discoveries and allowed smaller research groups to contribute to our understanding of cosmic rays. The citizen science aspects of cosmic ray research are particularly charming. Simple cosmic ray detectors can be built by students and amateur scientists, contributing to our understanding of these particles. Schools around the world participate in cosmic ray monitoring programs, with students learning physics by detecting the same particles that professional researchers study with billion-dollar instruments. There's something wonderfully democratic about a phenomenon that can be studied with equipment ranging from a simple cloud chamber made with dry ice and alcohol to sophisticated underground observatories. This accessibility has made cosmic rays a gateway for many people into physics and astronomy. The idea that you can detect particles from space in your own backyard captures imaginations in a way that more abstract physics concepts sometimes don't. It's tangible mystery, invisible but real, exotic but accessible. The study of cosmic rays has also revealed unexpected connections between seemingly unrelated fields. Archaeologists use cosmic ray-produced isotopes to date ancient artifacts. Geologists study cosmic ray interactions to understand how landscapes change over time. Even economists have found applications for cosmic ray data in studying statistical correlations and random processes. These cross-disciplinary connections highlight one of the most beautiful aspects of cosmic ray science, its universality. Because cosmic rays affect everything on Earth, they provide a common thread that connects diverse fields of study. They remind us that science is not a collection of isolated subjects, but an interconnected web of understanding. The environmental aspects of cosmic ray research have also become increasingly important. As we've learned more about how cosmic rays interact with the atmosphere, we've discovered their role in atmospheric chemistry and climate processes. The ions created by cosmic rays can influence cloud formation, potentially affecting weather patterns and climate over long timescales. Some scientists have proposed that variations in cosmic ray intensity, perhaps caused by changes in solar activity or our solar system's movement through the galaxy, might contribute to climate variations on Earth. While this remains an active area of research and debate, it illustrates how cosmic rays connect us not just to distant astronomical events, but to the immediate environment we live in. The implications for climate science are still being explored, but they're potentially significant. If cosmic rays do influence cloud formation, then changes in cosmic ray intensity could affect global temperatures. This would mean that events occurring in distant parts of the galaxy could influence the weather on Earth, creating connections across vast scales of space and time. This possibility has captured the attention of both scientists and the public, though it's important to note that any cosmic ray effects on climate would be subtle compared to other factors like greenhouse gas concentrations. Still, the idea that stellar explosions thousands of light years away might influence the formation of clouds over your hometown is a compelling reminder of our cosmic connections. The biological effects of cosmic rays continue to fascinate researchers as well. While the radiation dose from cosmic rays at Earth's surface is relatively low, it's not zero. Every living thing on Earth receives a small but measurable dose of cosmic ray radiation throughout its lifetime. This natural background radiation has been present throughout the evolution of life on our planet. Some scientists have speculated that cosmic rays might have played a role in the origin of life itself. The high-energy particles could have helped drive the chemical reactions that led to the formation of complex organic molecules in Earth's early atmosphere and oceans. While this remains speculative, it's intriguing to think that the same stellar explosions that created the heavy elements necessary for life might also have provided the energy needed to organize those elements into living systems. The genetic effects of cosmic rays are also being studied with new interest. While most cosmic ray interactions with DNA are harmless, occasionally they cause mutations that can be passed on to future generations. These cosmic ray-induced mutations are part of the natural variability that drives evolution, providing the raw material for natural selection to work with. In a sense, cosmic rays have been editing the book of life on Earth for billions of years, making tiny changes to the genetic code that occasionally lead to new traits and capabilities. You could say that cosmic rays are co-authors in the story of evolution, invisible editors working on a timescale far longer than human civilization but shorter than geological epochs. This evolutionary perspective on cosmic rays raises fascinating questions about life elsewhere in the universe. If cosmic rays play a role in driving evolution on Earth, they might have similar effects on other worlds. Planets orbiting in different galactic environments, with different cosmic ray intensities, might experience evolution at different rates or in different directions. A planet near the galactic center, where cosmic ray intensities are higher, might experience more rapid evolutionary change than a world in the sparse outer regions of the galaxy. Conversely, a planet with a stronger magnetic field or thicker atmosphere might be more protected from cosmic rays, leading to more stable, but perhaps less innovative evolutionary processes. These are speculative ideas, but they illustrate how cosmic ray science connects to astrobiology and the search for life elsewhere in the universe. As we discover more exoplanets and study their environments, cosmic rays will likely become an important factor in assessing their potential habitability. The technological applications of cosmic ray research continue to expand in unexpected directions. The techniques developed for detecting cosmic rays have found uses in medical imaging, where similar principles are used to peer inside the human body. The data analysis methods used to extract cosmic ray signals from noisy data have influenced fields ranging from finance to artificial intelligence. Perhaps most remarkably, cosmic rays themselves have become tools for studying things that would otherwise be invisible. Cosmic ray muons can penetrate deep into solid matter, making them useful for imaging the interiors of volcanoes, pyramids, and other large structures. This technique, called muon tomography, has already revealed hidden chambers in ancient monuments and provided insights into volcanic processes that would be dangerous or impossible to study directly. The ability to use cosmic rays as a natural imaging system highlights the remarkable properties of these particles. They're energetic enough to penetrate kilometers of solid rock, yet they interact weakly enough that most pass through without being absorbed. This makes them ideal probes for studying dense materials that would stop other forms of radiation. Security applications of cosmic ray detection are also being developed. Because cosmic ray muons can penetrate heavy shielding, they can be used to detect hidden nuclear materials or other contraband that would be invisible to conventional screening methods. The same particles that tell us about distant supernovas might help keep us safe here on Earth. The philosophical implications of cosmic ray science extend far beyond the technical details. These particles represent a form of information that connects us directly to events occurring throughout the universe. Every cosmic ray carries data about its journey, encoded in its energy, direction, and composition. Learning to read these cosmic messages has taught us about stellar evolution, galactic structure, and fundamental physics. But perhaps more importantly, cosmic rays remind us of our place in the cosmic story. We're not separate observers of the universe, but active participants in it. The same nuclear processes that created the cosmic rays streaming through us also created the elements that make up our bodies. We're made of stellar debris, animated stardust, that has somehow learned to contemplate its own origins. This perspective can be both humbling and inspiring. Humbling because it reminds us how small we are in the context of the galaxy, how brief our individual lives are compared to cosmic timescales. But inspiring because it reveals our deep connection to the universe, our participation in processes that span space and time on scales we can barely imagine. The future of cosmic ray science promises even more remarkable discoveries. New detector technologies will allow us to study cosmic rays with unprecedented precision and sensitivity. Space-based observatories will provide cleaner data, free from the complications of atmospheric interactions. Advanced computer simulations will help us understand the complex processes that accelerate cosmic rays and guide them through the galaxy. The multi-messenger astronomy approach, combining cosmic ray observations with gravitational waves, neutrinos, and electromagnetic radiation, will provide new insights into the most energetic events in the universe. When we detect gravitational waves from colliding neutron stars or black holes, we'll also be looking for cosmic rays from the same events, building complete pictures of these cosmic catastrophes. Machine learning and artificial intelligence will help us find subtle patterns in cosmic ray data that human analysts might miss. The enormous datasets produced by modern cosmic ray observatories contain information that we're only beginning to extract. Advanced algorithms might reveal new types of cosmic ray sources or discover unexpected correlations that lead to breakthrough discoveries. The search for cosmic ray sources will continue with new urgency, The mystery of where the highest energy cosmic rays come from remains unsolved, despite decades of investigation. New detector arrays covering vast areas will provide better statistics and potentially identify the cosmic accelerators responsible for these extreme particles. The connection between cosmic rays and dark matter will also be explored with growing sophistication. If dark matter particles occasionally interact with cosmic rays or decay into detectable particles, cosmic ray observatories might provide our first direct evidence of this mysterious substance that makes up most of the matter in the universe. As human activities expand beyond Earth, cosmic rays will become increasingly important for space exploration and settlement. Understanding cosmic ray radiation will be crucial for protecting astronauts on long-duration missions to Mars and beyond. This knowledge might also inform the design of habitats on other worlds, where the protection of Earth's atmosphere and magnetosphere won't be available. The study of cosmic rays might even contribute to the development of new energy technologies. While the energy flux of cosmic rays at Earth's surface is too low for practical power generation, the principles behind cosmic ray acceleration might inspire new approaches to fusion energy or particle beam technologies. But beyond all the practical applications and scientific discoveries, cosmic rays will continue to serve as messengers from the deep cosmos, carrying stories of stellar death and galactic violence, of magnetic fields and shock waves, of the fundamental forces that shape the universe. They connect us to the stars in the most literal possible way, creating physical links between our bodies and the distant sources that created them. In the quiet moments before sleep, when the day's activities fade and consciousness begins to drift, cosmic rays continue their ancient vigil. They stream through your dreams as they've streamed through the dreams of every human who ever lived, invisible companions on the journey from wakefulness to rest and back again. They're proof that even in our most private moments, we're never truly alone but always connected to the vast, energetic, beautiful universe that surrounds us. The story of cosmic rays is ultimately the story of connection between Earth and space, between past and present, between the smallest particles and the largest structures in the universe. They remind us that boundaries are often illusions, that the familiar categories we use to organize our experience here and there, self and other, earthly and cosmic, are conveniences rather than fundamental truths. As you drift towards sleep tonight, carried along by the gentle rhythm of these words, cosmic rays will continue their patient work, editing the story of life with their gentle touch, carrying messages between the stars, connecting your dreams to the dreams of the universe itself. In the morning, they'll still be there, invisible but faithful, reminding us that we live in a cosmos where everything is connected, where every breath we take is part of a story that began with the first stars and will continue long after the last ones fade away. And so, dear listener, we come to the end of our gentle journey through the invisible rain from space. We've drifted from Victor Hess's balloon rides high above Austria to the sophisticated detector arrays that now span continents. We've followed cosmic rays from their violent births in stellar explosions to their quiet passage through your body as you listen to these words. We've discovered that these invisible messengers connect us not just to distant stars, but to the very processes that created the elements of life itself. Tonight, as you settle into sleep, perhaps you'll think differently about the darkness around you. It's not empty space, but a sea filled with travelers, particles that began their journeys in the hearts of dying stars, that crossed the galaxy for millions of years, that passed through the magnetic shields of our planet and the filtering layers of our atmosphere, all to arrive at this precise moment when they stream gently through your dreams. There's something profoundly comforting about this cosmic constancy. While everything else in our lives changes and shifts, while civilizations rise and fall, while species evolve and ecosystems transform, the cosmic rays keep falling like patient rain. They've been our silent companions since before the first life stirred in ancient oceans, and they'll continue long after our sun becomes a white dwarf and the last light fades from our corner of the galaxy. In a universe that can seem vast and indifferent, cosmic rays remind us that we're woven into its very fabric. You're not just observing the cosmos from a distance, you're participating in it, breathing it, being gently sculpted by it with each passing moment. The same stellar furnaces that forge the iron in your blood also created the shock waves that accelerate cosmic rays. The same supernovae that scattered heavy elements through space also sent these invisible messengers on their long journey to reach you here, now, in this quiet moment before sleep. The scientists who study cosmic rays often speak of them with an almost poetic reverence. These researchers spend their careers building cathedral-sized detectors underground, creating arrays of instruments that stretch across entire countries, all to catch glimpses of particles so small they make atoms look enormous. They do this because cosmic rays are letters from the universe itself, written in the language of energy and matter, telling stories of places so distant and events so violent that they challenge our imagination. But you don't need a PhD in physics to be touched by the wonder of cosmic rays. Every time you look up at the stars, every time you feel that sense of awe at the vastness of space, you're responding to the same fundamental truth that cosmic rays represent. We're all part of something much larger than ourselves. These particles prove it in the most literal way possible, creating physical connections between your body and the distant reaches of the galaxy. The children who build simple cosmic ray detectors in science class, watching for the brief flashes of light that reveal a particle from space, are participating in the same fundamental quest as the researchers at the world's most sophisticated observatories. They're all learning to listen to the quiet voice of the cosmos, to read the messages written in radiation and energy, to understand their place in the grand story that began with the Big Bang and continues in every moment. As our knowledge of cosmic rays has grown, so has our appreciation for the delicate balance that allows life to exist on Earth. Our planet sits in a kind of Goldilocks zone, not just in terms of distance from the Sun, but in terms of cosmic ray exposure. We receive enough cosmic radiation to drive genetic diversity and evolution, but not so much that it overwhelms our DNA repair mechanisms. Our magnetic field and atmosphere provide just the right amount of shielding, filtering out the most dangerous particles while allowing the gentler messengers through. This balance isn't accidental, but the result of billions of years of cosmic evolution. The same processes that created cosmic rays also created the conditions that allow us to exist. We live in a universe that's simultaneously violent and nurturing, chaotic and ordered, vast and intimate. Cosmic rays embody all these contradictions, carrying messages of stellar death that somehow contribute to the continuation of life. The future will undoubtedly bring new discoveries about cosmic rays, new mysteries to unravel, new connections to explore. Perhaps we'll finally identify the sources of the most energetic cosmic rays, or discover new types of particles in the cosmic ray spectrum. Perhaps we'll find definitive evidence that cosmic rays influence climate, or uncover their role in the origin of life on Earth. Perhaps we'll even learn to harness their energy for interstellar travel, using the galaxy's own particle accelerators to power our journeys to distant stars. But whatever new discoveries await, the fundamental wonder of cosmic rays will remain. They'll continue to fall like gentle rain, carrying their ancient messages from the deep cosmos, connecting us to places and times we can barely imagine. They'll pass through the bodies of future generations, just as they've passed through ours, creating an unbroken chain of cosmic connection that stretches from the first stars to the last. In your dreams tonight, cosmic rays will accompany you on whatever journeys your sleeping mind creates. They'll be there as they've always been, invisible but faithful, carrying stories of stellar birth and death, of magnetic fields and shock waves, of the fundamental forces that shape everything we know. When you wake tomorrow morning, they'll still be streaming through the sunlight, still connecting you to the universe in ways both subtle and profound. This invisible rain from space reminds us that we're never truly alone, never truly separate from the cosmos that created us. We're temporary arrangements of stardust, animated by the same nuclear fires that forge cosmic rays, shaped by the same evolutionary processes they help to drive. In recognizing this connection, we find not diminishment but enlargement, not insignificance, but profound belonging to something vast and beautiful and endlessly mysterious. And perhaps that's the most beautiful truth cosmic rays offer us, that in a universe often described as cold and empty, we're actually swimming in an ocean of connection. Every moment of your existence unfolds within this gentle bombardment from distant suns, this quiet conversation between your atoms and the galaxy itself. It's a reminder that isolation is an illusion, that the boundaries we draw between self and cosmos are merely convenient fictions we tell ourselves to make sense of our experience. The poets and philosophers throughout history have searched for ways to express our relationship to the stars, often settling for metaphor and imagery. But cosmic rays give us something more tangible, literal threads of matter and energy that weave us into the cosmic tapestry. When William Blake wrote about seeing a world in a grain of sand and heaven in a wildflower, he couldn't have known that his words would one day find their perfect scientific expression in these invisible particles that carry the actual substance of distant worlds through every grain of sand, every wildflower, every living cell. There's something deeply satisfying about this convergence of poetry and physics. This moment when science catches up to the intuitions of artists and mystics who always sensed that we're more connected to the universe than our everyday experience suggests. Cosmic rays don't just confirm this connection, they embody it, streaming through our bodies at the speed of light, carrying messages that bypass our conscious minds and speak directly to our atoms. As you lie there now, feeling perhaps the weight of blankets, the softness of your pillow, the quiet rhythm of your breath, remember that you're also feeling something else, the gentle touch of cosmic rays, so subtle that it registers below the threshold of sensation, but so constant that it never stops. It's like being caressed by the universe itself, a tender bombardment that began before you were born and will continue long after you're gone. This perspective transforms even the most mundane moments into something sacred. Your morning coffee exists because cosmic rays help drive the evolution of the plants that learn to photosynthesize. The oxygen you breathe was forged in stellar cores and scattered by the same explosions that created cosmic rays. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it seasoned with the patient touch of particles from space. Even our capacity for wonder, our ability to contemplate cosmic rays and feel moved by their story, emerged from billions of years of cosmic ray interactions with our genetic material. In a very real sense, cosmic rays helped create the consciousness that now marvels at cosmic rays. We are the universe looking at itself, temporary arrangements of star stuff that have learned to appreciate the very processes that brought us into being. This isn't just beautiful, it's transformative. Once you truly grasp that cosmic rays connect you physically to the most distant reaches of space and time, it becomes impossible to see yourself as separate from the cosmos. You become not just a resident of Earth, but a citizen of the galaxy, not just a biological organism, but a conscious expression of cosmic evolution. And in those moments when life feels overwhelming, when the problems of daily existence seem insurmountable, cosmic rays offer a different perspective. They remind us that our troubles, however real and immediate, are playing out against the backdrop of something immeasurably vast and ancient. The same particles that witnessed the birth of our solar system are with you now as you navigate whatever challenges you face. There's a strange comfort in that continuity, in knowing that you're part of a story that transcends any individual difficulty. The scientists who dedicate their lives to studying cosmic rays often describe their work in terms that border on the spiritual. They speak of feeling humbled by the universe, of being moved to tears by the elegance of cosmic processes, of finding in cosmic rays a sense of purpose that goes beyond career or recognition. They're not just studying particles, they're participating in humanity's ongoing attempt to understand its place in the cosmos. This quest for understanding has brought us to a remarkable moment in human history. For the first time, we can not only detect cosmic rays, but begin to read the stories they tell. We can trace their origins to specific types of stellar explosions, map their journeys through galactic magnetic fields, measure their effects on Earth's atmosphere and climate. We're learning to speak the language of the universe itself, one particle at a time. But perhaps the most profound lesson cosmic rays teach us is about time. These particles carry within them the history of the galaxy, the chemical signatures of ancient supernovae, the energy patterns of long-dead stars, the magnetic fingerprints of cosmic events that occurred when the universe was young. They're living archives, mobile museums that preserve the story of cosmic evolution in their very existence. When a cosmic ray passes through your body tonight, it might be carrying iron atoms forged in a star that exploded billions of years ago, when the Milky Way was still forming its spiral arms. That iron might have spent eons drifting through interstellar space before being incorporated into the shock wave that accelerated it to cosmic ray energies. Now it's here, in this moment, sharing space with the iron in your bloodstream, two products of the same ancient stellar furnace, briefly reunited in the quiet darkness of your bedroom. This is time travel in its most literal sense. Cosmic rays don't just tell us about the past, they bring the past to us, delivering actual samples of ancient cosmic events to our doorstep. Every cosmic ray is a piece of deep time made manifest, a fragment of stellar history that has somehow survived the journey across space and time to reach you here, now, in this moment of quiet reflection. The study of cosmic rays has also revealed something beautiful about human nature, our irrepressible desire to explore and understand, even when the subject of our curiosity is invisible and the answers are difficult to find. The researchers who built the first cosmic ray detectors couldn't have imagined the sophisticated observatories we have today, just as today's scientists can only dream about the discoveries that await future generations. But the drive to understand remains constant, passed down like genetic memory from one generation of cosmic ray researchers to the next. It's the same impulse that led Victor Hess to risk his life in a balloon basket high above Austria, the same curiosity that motivates today's graduate students to spend long nights calibrating detectors in underground laboratories, the same wonder that might inspire some future scientists to develop technologies we can't yet imagine. This continuity of human curiosity is itself a kind of cosmic ray, an invisible force that propagates through time, carrying information and energy from one generation to the next, connecting past and future in an unbroken chain of discovery. The questions we ask about cosmic rays today were planted by the scientists who came before us, just as our work plants the seeds for questions that won't be answered for decades to come. And so, as you drift towards sleep, you become part of this great continuum, not just as a detector of cosmic rays, but as a participant in humanity's ongoing dialogue with the cosmos. Your wonder at these invisible messengers from space adds to the sum total of human curiosity about the universe. Your appreciation for their beauty contributes to our species' growing understanding of its place in the cosmic story. The cosmic rays streaming through your dreams tonight carry more than just energy and information, they carry possibility. The same processes that created them are still at work throughout the galaxy, still forging heavy elements in stellar cores, still launching particles into space at incredible energies. Somewhere in the galaxy at this very moment, a massive star is reaching the end of its life, preparing to explode in a supernova that will create the cosmic rays of the future. Those future cosmic rays might travel for millions of years before reaching some distant planet where other conscious beings lie in their own beds, listening to their own version of cosmic ray stories, feeling the same sense of connection to the universe that you feel now. The invisible rain from space connects not just different places but different times, creating a web of cosmic connection that spans the galaxy. In the end, cosmic rays remind us that we live in a universe where everything is connected. where the death of a star can influence the evolution of life on a distant planet, where particles too small to see can carry messages across distances too vast to comprehend. They teach us that we're not observers of the cosmos, but participants in it, not separate from the universe, but expressions of it. As sleep finally claims you, cosmic rays will continue their patient work, streaming through the darkness, carrying their ancient messages, connecting your dreams to the dreams of distant stars. They'll be there when you wake, faithful companions on humanity's journey of discovery, invisible reminders that we live in a universe far stranger and more beautiful than we ever imagined. Sweet dreams, fellow traveller in this cosmic rain. May your rest be gentle, your sleep be deep, and your dreams be filled with the quiet wonder of knowing that you're never alone, that you're always connected to the stars through these invisible messengers from the deep cosmos, these patient particles that link us all to the vast, magnificent, endlessly mysterious universe we call home.